This meeting is being recorded.
Hi everyone, good morning. So welcome to the webinar conducted by Innovit Technologies. So today's topic is create your own LLM. It is a category of a GenAI, and we are pleased to have Nishi Paul ma'am. She is one of the finest and she has the great expertise in GenAI and all the AI ML fields. She has worked with HSBC and so far we have covered total 4 webinars and this is our 5th webinar. Yeah, so over to you, Nishi ma'am. We can start.
Hello, thank you for this introduction. So this is our last webinar, and this webinar is on getting started with LLMs, where you will be coding your own LLMs. And I'm going to share my screen now. Okay, where is it? Okay, so today's topic is to get a hands-on with LLMs. Now, in our first webinar, we went through the generative applications that are available and how we can make use of that. Then in the second, we went through the concepts of machine learning. And the third, we went through the concepts of deep learning. And then we went through the concepts of transformer architecture, which is the basic building block for the generative models, and have understood how those works in our last webinar, that is the fourth one. And today is the final, which is on large language models. Okay. So getting started, I will just give a brief introduction on how the transformers are and why we need to use the pre-trained models when it comes to LLMs, and what this fine-tuning essentially implies. Now, if you find it kind of difficult in understanding, because here we are going to go through mostly on the LLM parts, like what are the components of it and how you can get started with the coding. About the models and the architecture, if you're finding it difficulty, you can go back to the previous webinars to take a look at it. So all the transformer models such as the GPT, BERT, BART, T5, etc. So they are all trained as language models. This means that they have learned vast amounts of raw text in a self-supervised manner. So this self-supervised learning, basically it is automatically generating the training objective from the model's inputs, that is, which are the text in our case. And so human labeling the data isn't required in case of the self-supervised manner learning procedure. So while these models like this GPT, T5, and BERT, and there are many llama. So while these models are acquiring a statistical understanding of the language that they are trained on, they are basically not suitable for any kind of special practical tasks or some kind of specific tasks that you might have at hand. So to address that issue, all the general pre-trained models, they go through transfer learning where they are being fine-tuned in a supervised manner, and there you can use, while the fine-tuning process, some human annotated labels, that is your output, and the input will be your textual data. We will see how that looks like in some time. So that's about the transformer, an overview, like why this pre-training and the fine-tuning means. So if I give you an example, you can think of a pre-trained model as ourselves only. Like we all have school degrees, we all have, when we were being taught everything at once. So we were pre-trained. Then we went to college where had taken up some kind of a special ED. That means we were fine-tuning ourselves on a specific task. So in this way, you can think of it, yes. Okay. So now, this is what the pre-trained model you can think of, right, in that way. So transformers are basically very large models, and while there are some kind of exceptions like the distal bird, which is a form of bird, but that is about 60 percentage lighter and it retains most of the characteristics of the bird. So transformers are otherwise they're very large models. So the common approach to improve the performance for a transformer involves increasing the model size or the volume of the pre-training data, or in some cases both. However, if you go on training such large models, then it would require you substantial amount of data, which can be very much expensive in terms of time and computational resources, and can also have a significant environmental impact. So just think that if each of the research team or the student organizations or company they have to train a model from scratch every time, then it would actually result in very enormous and avoidable global costings. Therefore, sharing language model becomes crucial. So when you're sharing models, what you are doing? You are distributing the trained weights, that is the learned parameters, the parameters about which we have already seen in the previous webinars. So by that, you can share your pre-trained models because it knows about the weightages, and on top of that existing model you can build your fine-tuned model. So it would reduce both the computational expenses and the carbon footprint that might associate with the model training as per your purposes. Okay, so pre-training involves training a model from the scratch with randomly initialized weights, starting without any kind of prior knowledge, and this process would thus require vast amount of data for the proper representation and learning, and it can take even several weeks because of the extensive training involved. And in contrast, the fine-tuning occurs after a model has already been pre-trained. And to fine-tune, you start with a pre-trained language model and then continue training it on a specific dataset which is tailored for your particular task. To give you an example, GPT model, I guess it's GPT 3.5 if I'm not very wrong. It has been trained for around 12 days continuously and it used several servers. So it's quite that much extensive performance. So that's why using the pre-trained models and fine-tuning them is very much essential. And this is what we are going to do in our practicals today. Okay. So this is what transfer learning is. Now, when you fine-tune a pre-trained language model for a specific task, you are basically building upon the existing knowledge. So the model already has a good understanding of the language. So it doesn't need to learn everything from scratch. Instead, it can focus on learning the specific nuances of the task that is at hand, such as recognizing the sentiments in the text or generating some kind of new text, that is some kind of creative writing. And this approach is basically called the transfer learning because it is involving transferring the knowledge from one task, that is the pre-trained one, to another task, that is the fine-tuned one. Now, transfer learning, it can be a highly efficient way to train the language models because it can significantly reduce the amount of data and computational resources that are required. That's why this transfer learning is important. Okay. Now let's go through the transformer models. Now in this transformer models in case of LLMs that we are going to go through, because transformer models are also utilized in the computer vision scenarios of tasks. Here we will be looking through the types of transformer models in LLM. There are three types basically. One is encoder only model, then decoder only model, and the encoder decoder model, which is also called as a sequence to sequence models. And based upon these types, the usage pattern differs basically. Now, when we were in the last webinar, we saw about the transformer architecture where you have these two parts. One is the encoder part, another is the decoder part. So in some models, we are solely using the encoder part. In some models, we're using the decoder, and in some, we are using both of it. So what is this encoder only model? These models are ideal for tasks that involves understanding the input, such as in the case of the sentence classification, in case of named entity recognitions, These are mostly getting used. Or in terms of the categorization also, these encoder models are good to use. Now, encoder models, it utilizes only that encoder component of the transformer. And at each step, the attention layers can consider all the words in the original sentence, and that allows for bidirectional attention. That means whenever you are concentrating on a single word, it will look into the words surrounding it as well. So if you want to focus on this words all, the attention mechanism is going to consider the other words which are surrounding it. It is going to learn the context on the basis of the surrounding words it is having. So that is a bidirectional attention. And these encoder models are frequently referred to as auto-encoding models. Now, during pre-training, these models are typically trained by corrupting some of the input sentences in some way, such as masking some of the random words, that is, just blocking some of the random words, and then challenging the model to reconstruct the original sentence. And then it calculates the loss, like the reconstruction of that original sentence with that word replaced, or the word which has been placed in place of the masked word, how much close it is to the actual word. In that way, it goes on fine tuning. Okay, and example of encoder only models are like BERT, Roberta, Distilbert. Okay, now going forward to the decoder only model. Now the decoder only models are sorry. So the decoder only models are suitable for generative tasks like the text generations. And decoder models employ only the decoded component of the transformer. And in this, the attention layers can access only the words that comes before the current word in the sequence. For example, in the decoder-only model, if you need to pass this complete sentence, that is use only decoder part of a transformer, if you need to pass this complete sentence into a decoder-only model, then the decoder will have access to the words prior to the words it is focusing on, right? Like if the use word is getting into the decoder-only model, then it has the knowledge of use only. I mean, it has knowledge of this word use. It is not having access to any of the words after that. Then only word is entering into the decoder model. Now the decoder model has access to use and then only. It is not having knowledge of any of the other parts. So this is what we mean when we say that the attention layers which are present in the decoder only model, it has access to the word that comes before the current word in the sequence. Often it is referred to as the autoregressive model, and they are trained to predict the next word in the sentence during the pre-training procedure. And normally this is being done using the masking format only. And these models, the decoder-only models, are particularly well suited for anything which is related to task or text generation tasks, like the chatbots or the GPT models. They are the very famous decoder-only models. So in the GPTs that you see, or the very famous chat GPT one, it is based out of decoder-only models. That is, it is not having the encoder part. Okay. Next is the encoder-decoder model or sequence-to-sequence model. This is also very much effective for generative tasks that needs an input such as translation or the summarization, which is very useful. Encoder-decoder model, also called the sequence-to-sequence as it is implied, it utilizes both the components of the transformer architecture, that is both the encoder and the decoder. Now, the encoder's attention layers can access all the words in the original sentence, while the decoder's attention layer can only access the words that comes before the current word in the sequence. So, the working structure of the encoder and decoder essentially remains the same. The concept remains the same. The way you are going to utilize it differs with the use cases. So retraining the sequence models often involves much more complex tasks than those which are available for the encoder or only the decoder models alone. Example of it is a T5 model, which is pre-trained by replacing random spans of text with a single masking token, and then training the model to predict the text that the mask token represents. So kind of the same concept goes here as well. Now, the sequence to sequence models are particularly effective for tasks like the summarization, translation, so the generative question answering, and T5 and Word is normally used for this. Like even in case of T5, there are multiple variations: T5 small, T5 big, T5 large, and in those cases, the number of encoder and the decoder layers you are utilizing differs. And accordingly, its precision also differs, and the model size will differ, of course. Okay. So the concept that is going around here is a bit tricky and interesting as well. But when it comes to coding, it's quite easier to code than it is to understand the concept and all the mathematical things that goes behind it. Okay. Now, transformer models are usually very large, right? With millions to tens of billions of parameters given, training and deploying these models are very complicated. Now, when some kind of new models are being released on nearly a daily basis, and each having its own type of implementation, each having its own way of training, like all the models, if you see the model card in the last webinars when I showed you in the Hugging Face, the model card will give you the complete detail of the model that you are using. There you will see that each of the models are being trained differently, they're implemented differently. And when I say implemented differently, what I mean is the number of layers, the basic number of layers remains the same. And on top of that basic number of layers, you are utilizing or introducing many more layers, which is essentially called as heads, that is changing your use case. We will see that in a minute, but the thing is, many new models are being released on a daily basis, and each are having its own implementation, and trying all of them out is not really an easy task. So this Hugging Face Transformer library was created to solve this problem because its code is to provide a single API through which any transformer models can be loaded, trained, and saved. And also you can go through all the model cards to see how it is being created or how it is being trained and how you can make utilization of that kind of a model. Okay. So the pipeline, what is the pipeline in case of a transformer model? And the pipeline in transformer means the pipeline function in the transformer library which is offered by Hugging Face. So a pipeline, it refers to as a series of steps which is involved in processing the text data using transformer model. And it typically consists of three main phases: pre-processing phase, model inference, and post-processing. So the pipeline, you will see that the pipeline is just a function, and inside of it, you are putting your data and you are placing the model. You do not have to do anything else. It will do all these three things for you: pre-processing, model inference, and post-processing. Pre-processing is converting the raw text into the format that the model can understand. Model inference is passing that pre-processed data through the transformer model that you will specify in order to get the prediction. And post-processing is converting the model's output into a human readable format. So in the pre-processing steps, what all things happen is the tokenization, numerical mapping, and additional inputs. And we will see it in the lab how all of these steps looks like. So the tokenization is basically breaking down the text into the smaller units, which we call as tokens. Now these tokens can be words, a part of a word, or even the punctuation marks. And the numerical mapping is assigning each of those individual tokens or the broken words or the broken units, some words for punctuations, assigning all of those individual units an integer, a unique integer basically. And additional input, what is that? Adding any extra information that might be helpful for the model to understand, such as the attention mask is being added, position in ratings is being added, and what are those? We will again see it in few minutes. But essentially, these are the pre-processing steps which are involved. So we will go through the pre-processing steps here. I'll zoom it for you a bit. Okay. Now, this here you see, yes, I think it's visible. Okay, so from the transformers, we are importing the auto tokenizer. So what is auto tokenizer? Auto tokenizer is a class from Transformers library that is providing a convenient way to load the tokenizer associated with different pre-trained models. Now over here, the model that we are using in this example is a distilled word based Sunkist fine-tuned SST2 English model. This is the name. So this model is particularly trained on the dataset of SST2 English. Okay. So the tokenizer for this model is specific to this dataset only. So when you are going to use it, the tokenizer should be the same as that of the model. So the model and the tokenizer should be the same. This thing we have to be sure about. So this from pre-trained method over here, this auto tokenizer dot from pre-trained, this from pre-trained method is used to retrieve the tokenizer's data based on this checkpoint name of the model. And this data is including this tokenizer's vocabulary, basically special tokens and all the other necessary informations that you might have. So here you see this is the checkpoint and the tokenizer, and when you are picking this up, the tokenizers are getting downloaded for you that you can use. This is tokenizer.json, config.json, vocab.txt according to this model, and then you can see how this tokenizer is like. We will see that in the lab as well. So first step is loading the tokenizer. The next step is to see or to pass the sentence to the tokenizer. So once you have the tokenizer loaded, you can directly place the input sentence into it. So this is the sentence, and inside of the tokenizer object, you are passing your sentences. And if you print it out, what you get is this input IDs, the attention mask. Okay, what are these things? We will see. Basically, the input IDs are the numbers associated with your tokens. This ones is words that is learning LLM is fun. These are getting converted, or these are getting tokenized, basically broken down into individual units, and those units are getting converted into some numbers, that is the tokens. And this is what are the input IDs associated with these ones. Okay. So the key point here is to remember is that you can pass one sentence or multiple or list of sentences basically, and you can also specify the type of tensor that you want to receive out of it whenever you are passing it to the tokenizer. So these are the sentences here. We have just passed the sentence. We have got this in this format, and you can also pass the sentences along with the return type. So here we have specified this return tensor as TF, that is the return tensor should be of the type of TensorFlow, and that's what we are getting over here. So this is a TF.tensor type, and over here it nothing as TF.tensor type was mentioned because this was just a normal NumPy array, but in this case it is a tensor type. So this return thing you can mention it over here. So if no type is mentioned, it is basically a list of lists inside the dictionary format. Now the output is a dictionary over here with two keys. Here you see this input IDs and the attention mask that we will see. Now the input IDs are the rows of integers, and it is representing each of the sentences. So this one here, it is the first sentence. This one is the second sentence. Same is in the return type as TensorFlow. You can see there are two types over here. This is the first sentence. This is for the second sentence. And here is the attention mask for this return type tensor as STF. And these are also in two parts. The first one is for the first sentence. The second one is for the second sentences. Okay. So first what you did is you did the loaded the tokenizer. Okay, and after loading the tokenizer, you created a tokenizer object by utilizing the auto tokenizer function from Transformers. And inside of the tokenizer object, you are passing your sentences. You are setting this truncation padding equal to true. We will see what is that, and you are setting up the return tensors. If you are not setting the return tensors, it will be a list which is inside a dictionary format, so it will be like a NumPy array kind of a thing. Then what you do is here, yeah, specific tokenizers that you can use. Okay, so the specific tokenizer usage I'm going to show you in directly in the lab. So we have seen that part where we have imported or used the auto tokenizer from the transformers, but here we can also make use of auto tokenizer. So either you can do from transformers import auto tokenizer, Or what you can do is from transformers input word tokenizer. So just as we have used the auto tokenizer and loaded the pre-trained model using the from pre-trained method, we have specific tokenizer classes too, which are specific to the model that we can use. And this is for the specific task that we will perform. So for bird, because we are going to use the bird model, we have got this bird tokenizer, which is specifically built for the bird architecture. Everything else will remain the same as with the auto tokenizer. That is, we will be declaring the sentences. There are two sentences that I have declared, and then we are initializing the tokenizer using the dot from pre-train. But here, instead of auto tokenizer, we have used but tokenizer dot from pre-train, and this is our tokenizer. Passing the sentences and then writing it as the truncation equal to true, specifying all these parameters, and then we see the input IDs and the attention mask separately. So when you're initializing it, this all will get downloaded, but it will be downloaded for once and then it will be cached in your system so that from the next time you do not have to, from the next time you are utilizing the same tokenizer, you do not have to download it. It will be picked up from the cache folder directly. Okay, so on printing the input IDs and the attention mask, which is related to this sentences that you have placed as the tokenizer, you got this tensor input IDs over here. Okay, so did you observe something here? In the number of words in the first sentence here is 5, right? The smart word is best word. The number of word is 5. But the token generated for this are 8 with 0 padding. So there are 1, 2, 3, 4, 5, 6, 7, 8 tokens and zeros. These zeros are basically for the padding purposes. So 5 words resulting in an array of 8 dimension input ID tensor. Why so? So let's take a look at the tokenization process in detail, like how this tokenization is taking place. Okay. The tokenizer that you have initialized, it has got this function of dot tokenize. And if you pass the sentence directly into this dot tokenize, you would observe something like this. Smart word is best word. Okay, it is getting divided. It is getting formed into tokens. Okay. Now here for the second sentence, you are getting the tokens as such. Now the second sentence was that weekdays are tiring. I love to work. I have to work. Okay. Now here, if you see, when you're tokenizing this sentence, this tiring is getting divided into two parts. This is tie and then hashtag RING. Why is this happening? Because the tokenizer that we are using is not having the knowledge of tiring as a whole probably, but it has knowledge of tie, TI and RING. So it is dividing your word into two parts, okay, or into two tokens. Okay. So we have previously seen the output of the tokenizer that was having the input IDs and the attention mask, right, that I have mentioned multiple times. So let's understand now what these input IDs are. Okay. So first we need to encode the text into numbers for that reason. And in order to do that, these tokens that we have formed after this tokenize step, we can utilize those tokens into the function of convert tokens to IDs. And we are utilizing the same word tokenizer object. So that tokenizer dot convert token to IDs, inside of it we are passing our word tokens and then we are receiving the input IDs. And for the second sentence also we are doing the same and we are getting this input IDs. Okay. So here, if you observe one thing, it says smart work is the best work, right? So work is repeating two times. In this case, we can see that 2147 is actually implying the work, or I can say that the work is mapped to this ID or the input ID of 2147. Even in the second one, that is when we did this one tokenization, here also we have this work at end, and here we can see it is 2147 is present in the input ID. Okay, so this is what input IDs are, and you can decode it also. Tokenizer or decode pass the IDs, and it will be decoded into your sentence as before. Okay, so Thus, when you are using this tokenized function, you can see that every part of the sentence is getting splitted into this individual chunks, and this splitting is dependent on the vocabulary of the tokenizer that you are using, and then you can convert it into the IDs. It will give you an idea of which word is corresponding to which of the IDs. So we can see that the input IDs are exactly the same as we got utilizing the tokenizer directly. So we did nothing. Here we just passed the sentences and the tokenizer has done all these things for us. So these two steps, first tokenize it, then convert it. We do not have to perform anything else. We can just pass it directly and we will get the same thing as we are getting here in two steps. Okay. So when you are passing this input IDs to the decode method of the tokenizer, you are again getting the sentence back. Right. Okay. So this is what the input IDs are. Before moving on to the padding or the truncation, I would like to see if anyone is having any question, or are we fine? Okay, so if you're having any doubt or any question, you can stop me and ask, and I will continue with our project work. Okay. So this is what the tokenization process is. I think up to this point, tokenization process is not yet ended. It is just the input ID part. But I think up to this point, you are okay with it. Okay. Utilizing the specific tokenizer, and we're looking into details, so you know what this is, the input IDs and the tokens. So up to now, what we know, up to now we know about the input IDs. Now we will know a bit about the padding and the truncation concepts before we move on to the attention mask. That's necessary. Why so? We will see. But before that, let us get an understanding of batching first. So batching involves processing multiple sentences simultaneously through the model, allowing the model to handle multiple sequences at once. So constructing a batch with several sentences is basically as straightforward as with a single sentence. However, the challenge arises whenever the sentences in a batch are of different lengths. And since the tensors requires a rectangular shape, you cannot directly convert a list of input IDs into a tensor without addressing that issue. So in our example, like we have one sentence with 5 words, another sentence with 8 words. Tensor cannot handle the mismatch in the sizes. So it has to be of similar types. It has to be of a rectangular shape. If I consider all of it together, so we need to take care of that before we can pass it to the model. So to manage this varying sentence length, we typically use padding to ensure that all the inputs are having a consistent shape. And padding ensures that for us that all the sentences will have a similar length by adding a special token which is called a padding token to the shorter sequences. For example, if you have a 10 sentence each with 10 words and one sentence with 20 words, then padding will extend the shorter sentences to match the length of the longest sentence, which is resulting in an all sentences having 20 words. The padding token ID, it can be accessed using the tokenizer.padded token ID, and with this we can process the sentences individually and in batches through the model. Okay, let's see in example now about the padding. So this is tokenization with padding, and I have written the same steps again and again for you to understand it better. Okay, so here again I'm picking up this auto tokenizer. You can also do it as a BERT tokenizer just in the first example. Okay, and the sentences remains the same. So autotokenizer dot from pre-trained, we are utilizing this model word based uncased. And now what we are performing is tokenizing each of the sentences individually. We are not passing it into the tokenizer, but individually tokenizing the sentences. It would be the same. You can try with that. However, we are doing it in this way because we want to see how this padding looks like. So tokenizing the sentences, converting it into input IDs and appending all of it into the token list, and this is what we are getting. Okay. After that, this is our shorter sentence, dividing it up. The first one, and this is the longest sentence, second one. And you can see that the shorter sentence is having 6 tokens, the longer is having 9 tokens. So in the shorter sentence, you can extend it. How? By adding the padded tokens. So the tokenizer dot pad token ID multiplied by 3 is basically will give you the 9. Why so? Because I can see the longer sentence is having 9 words, but the shorter is having 6 tokens or numbers or input IDs. So I have to match it to 9. That's why I did the multiplication by 3 and I utilized this pad token ID. And this pad token ID is basically 0 and it is coming with the tokenizer function, the word tokenizer function only. So with the object you can access it. So the shorter sentence and you are extending it with this extra 3 parrot tokens and then you can see the lengths are similar. So both are 9, 9. Now this is not a rectangular shape, right? This 6, 9. And this 9, 9 is uh, more of the required shape that is needed for the tensor transformations. Okay. Okay. So now this thing you can pass into the model. Okay. So here you see that the two sentences are of similar length and now we can use it to train the model of this one. Here again we are utilizing a different model. This is a Distilbert based uncased model. We are not utilizing the same model for a reason. Let's see what is that or why is that. So if you go back to this model summary, you can see what this model is made up of. This Distilbert model. Okay. Now, let me go to the, okay, let me go below. So the shorter sentence that we have, the shorter sentence there, this is the padding thing and the type of the shorter sentence is list, okay, fine. And now what we are going to do is convert it into tensor. So T constant, if you pass the shorter sentence into this one, you are ending up at a tensor which is of shape 9. Yes, this is of length 9. So now this is a tensor for us which is of shape 9. And now here you see the model. That is, you're passing it through the model. But the model is what this Distilbert that we are using. This is not a BERT model, but a Distilbert model that we are using in order to understand the concepts. So here you see that it is giving you some numbers. What are those numbers? So, okay, so let me go through line by line about this one. The model is referring to the pre-trained language model that we are using. Okay, this tf.constant shorter sentence that we are utilizing here, this is basically creating a TensorFlow constant tensor from this list. Okay, now when you are passing it into the model, this is basically calling the model's forward pass, which is passing the input tensors as an argument, and the model is processing that input and is returning some output tensor. Okay, so this is the output tensor that you're getting out of it. Now, if you want to get the logits only, these are the logits. Okay, logits are basically the calculation, the model output calculation. Okay, this is representing the raw output of the model before the final activation function. So you have picked up your sentence, you have converted it into the input IDs, and you're then passing your input IDs directly into the model, and then you are checking out the logits out of it, which is the raw output of the model. So what do you see here? These are the logits. Now this logits doesn't make much sense. So that's why we pass this model into the activation function. Okay. Okay. So getting back to our previous ones, the token list over here, uh, including both the sentences now. Okay, so here you see in the token list, the shorter sentence and the longer sentence joining both of it together is our batched sequence. Okay, so for the first sequence, we are applying the same thing, getting it inside the model. That is this logits.numpy. We are basically converting it. We want to get the numbers out of it. So these numbers, the logit numbers, we want to get only the numbers. So this is inside the logit and this is inside the numpy as you see. So we want to get the numbers out of it. So for the first sentence, if you see, the model output logit is this. For the second sentence, the model output logit is this. But when you join both of the sentences together, you are ending up with a logit like this. Right. So these two are coming as similar. There is no problem. Why there is no problem? Because when you are adding these token IDs and you're utilizing it both together, the padding is automatically getting added. Okay, if it is not very much clear maybe to you, but let us see where the problem is if the padding is not there. Let's see. first an example and then I'll explain it further. So let us declare one sentence over here as is 10 10 10. This is a second sentence 10 10 and this is a batched sentence. Okay, here we are just writing this token ID, tokenizer dot pad token ID, and then we are performing the similar steps as before. That is converting it into the constant, finding, passing it through the model, finding the logit numpy value of it. Okay, something unusual is happening here. What is that? For the first sentence, you can see these are the logics, and this is exactly the same as we are getting when we are using that in the batch. But for the second sentence, this is the actual logic. But when we are using it in the batch, the numbers are changing. Exactly the reason for which we need to learn about the attention mask. Now here, it didn't happen because when you are performing it using the model TF constant token list together, the paddings are getting added automatically so that it is so that both the sentences are coming at the same length, that is zero zeros we have added, they're coming at the same length. Now in this case uh, we haven't introduced any attention mask explicitly. So when this kind of tokenizer dot pad token ID, we are adding it to the batched input and then passing it through. These two are basically the model will look into add like differently. They are not the same for the model. So from here, basically, we can see that there is an issue with the logics which is present in our batched predictions. The second row should essentially match with the logics for the second sentence, but the value is completely different. And this is because the transformer models are using the attention layers to contextualize each of the tokens, and these layers consider padding tokens as they attend to all the tokens in the sequence. So to ensure the consistent results when processing the individual sentences of varying fields in the batches with the padding, we need to instruct the attention layer to ignore the padding tokens. And this is achieved using the attention mask. So if I let you know it in the lame terms, it is like there will be padding tokens. The padding tokens are required for it to be of a rectangular shape so that the models can accept it. The tensors has to be of that shape. And then these padding tokens are not adding any specific value to your output. That's why the model needs some method to know that these are the padding tokens and I should not be putting any attention to those padding tokens. That's why this attention masks are essential. So let's see what is that. Here we can see the sequences batched ID and the model. Okay, fine. But here we can see that there is an additional introduction of attention mask. What we are seeing is that 111110. That means this 111 is corresponding to the data that the model has to pay attention to. This 11 is corresponding to this two data that the model has to pay attention to. And in the batches, I have just introduced a token, a pad token, why so? Just to make it a rectangular shape. So for that, the attention mask should be 0. That is, do not pay attention to this token ID. Okay, this is just for making it making the ship compatible. Otherwise, this is not putting any importance to us. And when you do that, you can see that the numbers are actually matching, right? So the transformer models, uh, this is what the transformer models are. So this in the transformer models, these attention masks are basically crucial for handling the variable length input sequences and preventing the model from attending to the parrot tokens. And this is ensuring that the model is focusing on the relevant information and generates more accurate outputs. And this is also used for preventing information leakages, like in case of the autoregressive models. Okay, and the model should only attend to the previous token and not the future ones. Okay, and the attention mask is basically it will always be binary matrix where the 1 will indicate the real token and the 0 will indicate the pairing token. Okay, so this might get a bit difficult to understand at first, but you need to go through these concepts multiple times because these are bit tricky and this is essential to understand because when you will be fine tuning your own LLMs, your data has to be properly uh, encoded. That is that should be properly passed to the model. Otherwise, if you are putting on garbage into the model will give you out garbage and you will see the accuracy to be reducing. That's why I'm putting on more pressure on the parts while we will be doing the other projects like this paraphrasing, which is similarity checking, and for the sentiment analysis that I'm going to show you, those will become much more easier to understand if you put on more pressure into these encoding parts. Okay. Now, there are multiple ways of padding. Okay. So the transformer models are having a limit on the length of the sequences that they can process. And most of the transformer can handle about 512 tokens, and some can handle 1024 tokens. And in nowadays, the higher models like the GPT-4, they can handle about 32,000 tokens and even more maybe. So normally, in general, most of the models are handling up to 512 or 104 tokens. Okay. So to address that kind of an issue, that there is a limitation of the number of tokens that you can pass, there is a limitation to the data that you can utilize. You can either use a model which is designated for the, or which is designed maybe for the longer sequences, such as the long forms, or maybe you can truncate your sequences. If the truncation comes necessary for you, then you can manage that by specifying the max sequence length parameter, and you can handle the differences in the sequence length by using different padding styles as well. So there you will see the multiple ways of padding. So up to this point, I hope everything is clear. Okay, since there are no queries, I can see, I'll continue. Okay, so there are multiple ways of padding, and this is to ensure the limitation on the sequence of lengths and that the sentences that you're using are all of the same length. Okay, now the types of padding. Padding sequences can be up to maximum sequence length, up to the model's maximum sequence length, and up to the specified maximum sequence length. So when you write the padding as longest here in the tokenizer object, it will pad the sequence up to the maximum sequence length that you have in your data. Like I'm having this hello world over here, and here I'm having 1, 2, 3, 4, 5, 6 tokens. So this hello world will have a lot of zeros at the end that will pad it to match with the first input sentence. And these are the attention marks, as you can see right now. These zeros are basically referring to the padded tokens in the second sentence, and the model do not have to put an attention at. And then you see another type of padding, which is the max length. The max length padding argument is used when you want the padding to be of the model's maximum length. So some model can accommodate 512 tokens, some can accommodate 1024 tokens, so it will do the padding accordingly. So here when you have written this max length, and we are using over here digital bird, so you can see this model input. When you are passing this input IDs of the zero, that is, you are basically checking out for this one, what is happening with this one. When we are using this padding as the max length, you can see this is 512. So there are so many zeros that has got added just at the end of it. So you can remove this lane when you will try this out, remove this lane, try to print it out, and then you will see so many zeros are getting concatenated with this list. Okay, so normally in practice, we do the padding equals to longest when we do it in batches. Okay, normally this max length is not being done because that is a lot of space wastage. There are a lot of zeros coming up, and then you can specify the max length as well. So padding equal to the max length, and then max length is equal to 5. So it will truncate it to 5. When the max length was not specified, you can see you can see that there were 4 zeros at the end, and in this case there will be many more zeros. So if you specify this max length explicitly, it will just do the padding up to that point. Okay. Now, similarly, there is another concept called as truncation. So, truncations are also needed. Why so? Because let's say that you are utilizing this model of Distilbert, which has got the capacity of 512 tokens. Now, you are passing it some big paragraph, which is about 1,000 words, and of course, it is going to exceed 512 token limit. So, in that case, automatically the rest of the words is going to get truncated out, or the model will just reject that. So, this truncation knowledge is actually necessary. Now, over here, the truncations are of two types. One is the model's maximum sequence, maximum length, and the second one is the longer, that is truncating the sequences which is longer than the specified maximum length. That is, when you are writing this truncation equal to true, what it is going to do is truncate the sentences which are longer than the model's maximum length. That is 512 or 1024. But in this our case, our example, it is fine because we're not having um, that much of numbers or that much of words. And if you do write over here this max length equal to 5, then it is going to truncate up to the 5 only. So in our first sentence, as you see this one and this one, number of words are getting truncated, right? So 212920242017 up to this we have got over here. Now here you see these two tokens, this 101, 102, 101, 102. What are these? These are the special tokens. So in the slide when I was showing you, I did say that there are some additional inputs that we need to place, and these additional inputs are basically the special tokens that helps the model understand about the context. Okay, so here the special tokens are CLS and SCP. These are added to the input sequence during the tokenization to provide additional context to the model, and these tokens are learned during the model's pre-training process, and it helps the model to understand the structure of the input, especially when it is dealing with multiple sentences or sequences. So the CLS token here you see, this is often used to represent the classification token for the sentence level task like the sentiment analysis. Okay, and the final hidden state is corresponding to this token is basically used for the representation for the entire input sequence. And this ACP token, the separator token, it is used to separate different sequences in the input, such as in the question answering or in the text classification with multiple sentences. So by adding all these special tokens, the model can better understand the relationship between the different parts of the input sequences and make it more accurate for the prediction part. Okay, so here by decoding the first one and by decoding the second one, you can see how it is like the CLS and the CCP. Okay, here it ends the tokenization process. So in case of tokenization, you need the tokenizer, then the sentences, then the padding, the truncation, and you can also specify the return tenses that we have seen before. Okay, so let's see the batching and padding. We know it, right? We know it now. The need for attention mask, we know it now. Attention mask, what is it? We know that. Multiple ways of padding, we just have seen. Multiple ways of truncation. Then there are special tokens. Okay, so what we know till now, we have imported the tokenizer classes, then we pass the sentences, we can do the decoding from those input IDs, we can initialize the tokenizers using this pre-trained method, and we got the input IDs and the attention mask also, and we know what are those. Okay. Next thing comes up is the model building, the fun part. So what these model buildings are. Now that we have the tokenized data set, we can take it to the next step, that is feeding the model. We can download the pre-trained model in the same way as we did with the tokenizer, and we have to use the same checkpoint only. By checkpoint, what I mean is, if we use the bird-based case, then it will be the bird-based case. If we use the distal bird, then it will be the distal bird. Now, while understanding the tokenizer, I have shown you two models. One is the distal bird, another is the bird. For a reason, because while doing the word, if you do this by yourself, you will see that the input IDs are not that this one is having only the input IDs and the attention mask. That is, the tokenization process is having the input IDs and the attention mask only. But when you are using this distill bird, it is giving you three results, three compositions. Where is that? Let's see. Yes, it is giving you three compositions. Another one is token type IDs. Now, all of the models will not give you input IDs and attention mask only. Some will give you some other parameters also that helps the model in the contextual understanding of the data. So this is what the distilbird is doing. Okay, and if you go through the model card of the distilbird, you will understand it more what this token type IDs are exactly. But most of the models are coming with this input IDs and the attention masks only. Okay. Okay. Next step is the model building. Okay, let's go through a bit of a theory before doing that. Now, We can download these ones in the same manner as we did with the tokenizer, but in this case, we need to use another class, which is TF auto model. Just like we have used the auto tokenizer, and for more specific ones, we have used bird tokenizer. In this case, also, we have the general ones, TF auto model, and we have the specific ones as well that we will see. So this TF auto model class is from the Hugging Face transformer libraries, and this also has a feature called as from pre-trained. Okay, and by using that, you can download the checkpoint that you like. Now, TF auto model class is handy when you want to instantiate any model from a checkpoint, and the from pre-trained method, it will download and instantiate the model using the same checkpoint previously that is used for tokenization, which should already be cached because we already did that, right? Now, TF auto model class is provided by Hugging Face Transformers library that simplifies the process of loading the pre-trained transformer models into a TensorFlow. It provides pre-trained model, provides it is access to the vast collection of pre-trained models, allowing you to leverage their powerful capabilities without extensive training. And the from pre-trained method is simplifying the process of loading the pre-trained model, right? Now you can customize the model's configuration too. That is, you can decide on how many layers to use, how many attention heads to use, or what will be the hidden size in order to fine tune it for the specific task. Okay, so this architecture consists solely of the base transformer models, the TF auto models basically. Okay, so let me go to that one to show you how it is like. It will be much more better. Okay, so from transformers, as you see, we are importing the auto tokenizer and the TF auto model, and the checkpoint we're using is word-based uncased. Tokenizer from pre-trained, same checkpoint model, from pre-trained, same checkpoint, but the classes we're using is different. The checkpoints will be the same, one for the tokenizer, another for the model, the classes. And after that, you can see the model summary, which is letting you know the number of parameters or the number of weights the model has been trained upon. So you can see it's very, very huge, right? So the sentences that we're going to use is the same. Now, in the previous tips, we have a detailed understanding of the tokenizer is, and you can do it in just a single line. That is sentences padding true, truncation to return tenses equals to TF. Now you know everything about it, what these are like, or what this means. And then these inputs, you need to just pass it through the model. It will give you the output. Okay, but the output that you see over here, these are not the output that you would expect, right? Here you see some kind of arrays. So what are these arrays basically? These arrays are the hidden states basically. So here, if I scroll down, you can see these are the 768 vector dimensions. And this means basically that for every sentence, it has a sequence length of 12, and one sequence length is having 768 feature space. So it is a 3D. Okay? It is a 3D array. If you go through these steps, you will see that from the output, the last hidden state, the shape, you see the 212, 768. So let us go one step ahead. That is, let's look into the first one because we have given only two sentences, right? The first, let's go back to the sentences. There are only two sentences, and the longest sentence has got 12 input IDs. So it has to be 12. Now those 12 are again represented into 768 dimensional space. And if you go inside and inside for the first sentence, we are seeing this. Okay, so for the first sentence, for the first input ID, let us see how it is looking like. It is a tensor shape of 768. So in the last webinar, I did explain that when there are some word tokens are getting converted into token ID, input IDs, which are the numbers, those numbers are again getting converted into a dimensional space. Okay, and this dimensional space is 768, which is a vector space basically. So this is the hidden state. Now these hidden states are valuable on their own, but these hidden states are again the inputs to another component of the model, which is called the head component. Okay. Now while the underlying architecture is remaining the same, but different tasks are addressed by employing various different types of heads. So what do I mean by that? You will see. This is the array structure, the array which is a diamond, which is representing your input into the dimension, the vector dimension space. Okay, this is the utilization of the TF auto model. Now, notice one thing: uh, we explicitly stated the usage of TF auto model. We haven't specified anything else. We haven't specified if it will be for classification, if it will be for question answering, if it will be for categorization. We haven't said anything. We have just used TF auto model, and that's why we have got this hidden state, which is of 768 dimension. But this is useful if you are very much, if you turn pro while working with it, you will know what to do with these hidden states after that. But as a beginner stage, I want to perform classification, but I don't know how to do that using from this TF auto model. So what we can do is we can just place a head on top of it. So when I say that these inputs that we have got from there, the hidden state of the model, this is acting as an input to another component of the model, which is called a head. So this is our head for sequence classification. So this TF auto model that we have used and the output of the TF auto model that you have seen, those 768 vector dimension space, is going to get in this for sequence classification here. Okay, so when you are writing it directly, the concept is to understand, but the working is very much easier. Like when you are writing it on code, it is quite easier, but when you have to understand the concept of it, it will be a bit tricky. So now I'm not using this TF auto model dot from pre-trained. I'm using TF auto model for sequence classification dot from pre-trained, and here you see the output is much reduced. This output is reduced to the logits. The logits, which is the last output stage that the model is going to give you. Now, what are the model hits? I will explain it a bit in a moment in our slides, but here you see that by utilizing this model head, this for sequence classification model head, all those inputs over, all those output over here that you see, this hidden state, this array, vast amount of array in the 768 vector dimensional space, are going through this head for sequence classification and are giving you this logits, that is this value. Okay, now these logits are also not much useful as a prediction. We will see what to do with that logits in a moment. Before that, if you want to see how the specific basic model architecture is like, then you can just do this. Like from transformers, we're importing bird config, and this is how the bird config is made out of, the basic one, the base architecture. And the vocab size of it is 30,522 words. Okay, fine. And we can also do it in this format, that is, we can directly import the TF bird model. Now, this TF bird model are just like the bird tokenizer, which is specific for the bird tokenize bird vocabulary. This TF bird model is also the specific for the bird architecture only. So this is going to give you the same kind of a thing, but here again we haven't specified any head, right? We have just used TF bird model, that is we're using the TF bird model architecture, but we haven't specified it will be for classification, it will be for question answer. We haven't specified any head. So what it is going to give us? It is going to give us the hidden state of 768 dimensions or so. As you can see, yes, here 768 dimensions. So we will move to the post processing. Post processing is basically giving you the final output. Okay, but let's first go through what this model hits is. Okay, so now, as you have seen how the outputs are like, the explanation or the definition will be much more easier to understand. So, given that extensive numerical output from the model heads are essential for interpreting all those numbers. They take a high dimensional vectors of hidden states as input and project them into different dimensions, typically through one or more or few of the linear layers. The transformer model's output is directly fed into the model's head for processing. The model comprises its embedding layers and many subsequent layers. And those embedding layers are basically transforming each of those input IDs, those numbers from the tokenized input, into a vector representing the corresponding token. And the following layer then uses the attention mechanism to process all those vectors and generate the final sentence representation. Okay. just the same as we have seen in this lab. So if you go through this lab by yourself, then you will understand each and every step how it is going on. Try to change the values over here and see how these are ending up. Okay. Now, Hugging Face transformers are having a lot of head architectures. Here we have used for sequence classification, but there are other head architectures like for multiple choice, for question answering, for token classification. So you can just make use of it, the use of the heads just at the end of this architecture points, and you will get to see the different formats. Okay. Now, we have seen how it is working like. These are the model conclusions basically. So using the TF auto model is advantageous because that is creating the checkpoint agnostic codes, ensuring that if your code functions with one checkpoint, it will work smoothly with another. And this holds true even if the architecture is different, provided that the checkpoints were trained for similar tasks. What this essentially means is if let's say you want to perform the sentiment analysis that we are performing and we are utilizing TF auto model, since the architecture is same, you can make use of the BERT for the sentiment analysis, you can make use of Roberta as well because the architectures are different but the task is the same. We are working towards sentiment analysis, but it's always a good idea to not use it in that way, but to use the specific models only. That will make your things easier for you. Okay, so here let's go through the post processing step as you now know about it. Right, so I have written the steps again. That is from the transformers we're importing this auto tokenizer, and then we are importing the model that is TF auto model for sequence classification with the head. And then we're using this checkpoint, then this is the tokenizer, initialization, this is the model initialization, then defining the sentences, passing the sentences into the input for getting the input IDs for tokenizing, and then passing these tokenizers into this model where we are getting this output, and these are the output logics. Okay, so everything you have learned till now or have seen till now is basically coming down to this much steps, and this is it if you are using the pre-trained model. Now the output that you are getting is not very much useful to us, right? We wanted to post process it. How we do that? Make use of the softmax function. So what the softmax function is, we had defined it in the last class. The softmax function is basically going to give you the probability scores, and we are passing the output logics, that is this output logic values or the last values into the softmax function from TensorFlow math module, and here we get the values. So if you see, the first sentence has got the highest probability to be belonging to this category, and the first category, what is the first category, we will also define it by our own, but here let's look into this first, the numbers. And the second sentence, we can see that the second category has got the highest probability. So what are these? If you use this config parameter of the model, that is model.config.id to label, if you do that, you will see that 0 is label 0, 1 is label 1. Nothing is specified. You can specify it on your own. So here you have used this bird base uncased. Again, I'm utilizing the same thing, doing the same thing, but now I am mentioning the config labels basically. What I'm saying that this is the model.config.label2id. The negative is 0, positive is 1, and we have to do the vice versa as well. That is ID to label. This is basically making the model understand what our labels are implying. And then again the similar steps, passing it to the softmax function. Here you got your predictions, okay, and now this function is basically picking up the highest value and mapping it with the labels that you have specified earlier. So what it is giving you, that learning LLM is fun, then we could have thought it is giving you positive, struggle to achieve better, it is also giving you positive. So that's how you can make use of the pre-trained LLMs. And here you have a sentiment classifier using a pre-trained LLM. So what happened if we have used BERT model directly? Basically, this is a pre-trained model and this is another pre-trained model. This is what you are getting. Okay, so The output results that you observe from here is basically the pre-trained model only, but in a different way. I have used this tokenization. Here, the different way of tokenization you can utilize, that is change this padding, change the max length, and see how these outputs are coming up. We will next see how you can fine tune it. Okay, so the accuracy will increase highly after the fine tuning procedure. Now the complete code is given here for you. The complete code is just up to this much. Okay, so up to this much, this is the complete code. And here I have just used few more examples that you can try out with more different models or the different checkpoints. This is how the pre-training is looking like. Okay, so these are the model conclusions. Okay, so what have we done till now? Till now, we have imported the tokenizers. Then we have done the imported the tokenizers models, and we have done the tokenization. We have passed through those tokens into the through the model. Then we have gone through the output, how the output will be like if you're not utilizing the head, and how it will be like when we are utilizing the head. And then we have decoded also the numbers into the languages, that is decoded the input IDs into the words, and have seen the predictions, how the predictions are like. Okay, next is the main part, that is, okay, the post processing step, you know it now. Next is the main part where we will be fine tuning the model. Okay, so I'll show you how this same thing, the sentiment analysis, is being done, the fine tuning. But before that, let us go through the paraphrasing. Paraphrasing is basically used when you want to find out the similarity of the sentences. Paraphrasing means that if these two sentences are similar or not, basically if these two sentences are equivalent or not, that is what a paraphrasing is. And for this purpose, we are going to use the MRPC dataset, which is a Microsoft Research Paraphrase Corpus dataset. That is an example from the dataset hub. Let's go to the lab to understand it better. So from the dataset hub, we are utilizing this MRPC dataset, and this is including 5,800 about like that pairs of sentences, each labeled to indicate whether the sentences are paraphrases or not. That is, whether they are conveying the same meaning or not, if they are similar or not. And we are also going to use a different data set that we will be downloading from online. That is, you can do it in the similar procedure as with this one. The same procedure, we can do that, okay? Fine. So this is how the dataset is looking like. The dataset has got this train, validation, and the test parts, and here you can see these two sentences, sentence 1, sentence 2, and label and indexes. Okay. So what is this dataset object? Let's go through this dataset object at first from this Hugging Face. Dataset object is important, and if you go through that Hugging Face dataset, you will get a lot of things like that to work with. So dataset object in Hugging Face, it is a Python object that is representing a collection of the data instances, and it is providing a convenient way to access and manipulate dataset for the machine learning task, especially in the context of natural language processing. And the dataset object is essentially a table-like structure where each of this row is representing a data instance and each column would represent a feature. Hugging Face dataset automatically caches or downloads the dataset for you, just like the tokenizers and the models. Okay. Now, in this one, we have used this dataset only. This is the Hugging Face datasets. When you are downloading it from the Hugging Face, it is a dataset dictionary object. Okay. So here what you see is that there are 3,668 pairs of sentences in the training set, 408 in the validation set, and 1725 in the test set. Okay. So the labels in our dataset, let us check those first. If you go through the first one, the first record from this training dataset, you see that the label is 1. So the labels in our dataset is already in the integer format. So we do not need to pre-process the labels. Okay. Otherwise, you could have done one-hot encoding, or you could have done label encoder for encoding the labels, but it is already in the numerical format. Now to determine which integer is corresponding to which of the labels, how we know that? We can examine the features of our trained dataset that would reveal the type of each column, that is by these features. So from here, you see that the label is represented internally as class label, and it is mapping the integer to the label names which is stored in this list. So not equivalent is basically 0 and the equivalent is basically 1. Okay, this is what this features is going to tell you. It is going to tell you about the data that you are using, the features of your data. Okay. Okay. Now, the same thing that we have done before, and since you know the concepts, from here on, it is going to be a bit easier to pre-process the data set. We have to convert it, right? Now, if you select a different checkpoint, like here, I have now used word-based cased. Till now, I was showing you word-based and cased. Now I'm using word-based cased. So if you use a different checkpoint, you might not have this token type IDs as well. So just like we have seen in the word-based and cased, there was no token type IDs. In the digital bird, there were, and in the word-based cased, there is, as we can see. Okay. So here the tokenizer, then this is how the tokenizer is like if you're passing it in pairs to see how this input IDs are like. And one thing to notice at this point is that when we are passing it in pairs, the tokenizers are kind of different. Here you can see this input IDs. The input ID is no longer separated. This input ID is, both of the sentences. If you're passing these two sentences, then we would expect two input IDs, right? I mean, two lists of input IDs. But here we can see one. Why? Because the task over here is we want to check the similarity. And word-based cased, whenever you are using this tokenizer of word-based cased, if you're passing these two sentences at once, it will automatically understand that you might be trying to do the paraphrasing task, and this is not a classification task that we have seen before in the pre-training ones. So how are you, or how the model is going to separate or learn that both of the sentences are different sentences by the utilization of token type IDs, right? So you have seen the token type IDs previously, but you were not able to understand what this was, right? So this is what the task of the token type ID is. This is basically separating out your two sentences. So this means that this is one sentence and this means this is a second sentence in your paraphrasing. And this attention mark is implying 111 because we need to go through all of the words, right? Okay. So this is a sentence one. If you pass it, then you will see this token type is 00. If you pass only the sentence two, then you see that the token type is 00. But if you're passing it together, then the model will understand that you're trying to do the paraphrasing and it will do accordingly. Okay, so these are the inputs. We are passing the sentence one and the sentence two. This is the inputs, and you can convert it into the tokens to see how it is like. It is like this. Right, so this last four, as you see, the token type ID is giving us last ones. So this separator is basically separating out the two sentences that you have in the paraphrasing technique. Okay, now here what we can do is tokenize the sentences in this format. This raw data set in the train sentence one, raw data sets train sentence two. We can tokenize it in this format where the sentence one and sentence two are the columns, but we are not going to do that. This approach will work effectively, but it has got a drawback of returning a dictionary with the keys such as input IDs, attention mask, token type IDs, where the values are the list of list. Okay. Additionally, it is going to require sufficient RAM to store the entire dataset during the tokenization, unlike the datasets from the Hugging Face dataset library, which basically uses the Apache Arrow files on disk, and it only gives the requested samples in memory. So that's much more efficient. And to maintain the data as a data set and to gain more flexibility as well, we would utilize another function from the dataset which is called as map. Now for that reason, we need to define a tokenization function which we do it in this format. Okay, so how the map method works, I will define it in a bit, but how it is like here, you are just doing the same thing. That is inside the tokenizer, passing the first sentence, passing the second sentence, and writing this truncation equal to true. You can also keep the padding, but I'm writing this truncation equal to true over here because in this dataset, more or less all of the data, all of the columns are the similar length, and it is going to get truncated to the same length only. But it's good to keep the padding as well. You can put it as well in here and try to see how the output is different from this one. Okay, So using this tokenization function, this records here, we are passing the data set, that is dataset.map tokenization function batched equal to true. So this is going to pass the data in batches to this tokenization function and then truncate or tokenize each of the records individually, and this is going to store your tokenized dataset. So what your map method is doing, the function is processing a dictionary such as the items in our dataset, and it would return a new dictionary with the key of input IDs, as you can see, attention masks, and the token type IDs. It can handle the dictionaries which is containing multiple samples, as the tokenizer is designed to work with list of 6 sentence pairs. Using the batch equal to true option with our map call, it will significantly speed up the tokenization process. Okay. Additionally, padding all of the samples to the maximum length, it will be inefficient in this case because I haven't given it over here. Why? Because padding is effective when you are doing it within each batch, ensuring that the padding is done to the maximum length for that batch in the entire data set. And this approach can save considerable time, of course, right? Now, here, how we apply this tokenization function to the dataset simultaneously is that when we are writing this batch equal to true in the map call, the function is processing the multiple elements of the dataset in batches rather than handling each of the element individually. Right, that is in your dataset, you are passing the data into the batch, and here all the records or all the samples that you have, it will get converted into the tokenized format. That is, you're passing it in the form of a batches, and it will get padded to the highest or the largest uh, maximum sequence length in that batch automatically for you when you're doing this batch equal to true, and the truncation equal to true is going to truncate the sentence. Though it's a good practice to write the padding equal to true, but not in all cases we require it for all the checkpoints. You can check it out how these are different. Okay. Fine. So these are the data sets that we are getting. The two sentences, the labels, indexes, input token type IDs, and the attention mask. Okay. Okay. So here I've said that you can do the padding, but this padding is going to decrease the efficiency of the system. It's good to have the padding, but it's going to decrease the efficiency. So what we can do? There must be some kind of an alternative that will keep the efficiency at high and will do the padding for us as well. Exactly for that reason, we are using the data collateral with padding. The concept is same as that of the padding, but a little bit of a twist is here. It introduces dynamic padding. So the function which is responsible for assembling the samples within a batch is called a collate function, and a default collator typically is converting the samples to this tensor and concatenates them, and it even recursively concatenates them for the list that occurs the dictionaries. So this is here we can see this data collateral with padding. So to test this new data collateral function, let us first select few of the samples, like what this collateral is. This collateral is basically going to do the padding for you because we haven't explicitly have done it over here, and that was not very much efficient. Though you can do it if it is a lesser number of records and less number of data, but the efficient way to do it is utilizing the data collateral with padding. Okay, so let us first pick up 10 records, and over there we are not utilizing these indexes and the sentences from this dataset that we have got. Why? So because these are the textual records that the model won't be able to understand, and we have got the representation stored in this three features already for the sentences. Okay, so here what you see that the input IDs, they are having different kind of lengths. For this 10 we are observing, so this 10 records are having different kind of a length. So what we need to do, we need to pass this complete batch into the data collator, and then you see that all of them are coming at the same shape. So all the records are coming at the shape of 69 over here, because the 69 is the highest, the maximum number of words that we have in this input IDs. So this process of utilizing this data collator with padding is becoming much more fast. Okay. So with our data sets and the data collector ready, we can basically integrate all of it. So write all of it at once. This is a tokenized data set. Train.2tf data set is a function. You can make use of this function to pass the columns that you want, that is attention mask, input IDs, and the token type IDs. The label column is the label. Shuffling, you would want to shuffling while training, and the collate function is the data collator. The batch size is 10, that you are passing 10 records at once as your batch. Okay. So what is the tokenized data set? At first, you are performing this tokenization and you are not placing the padding over here because you are going to use the data collator, which is much more efficient. And after this tokenized data set, you are utilizing this 2TF data set function from the Hugging Face library only. So that tokenized data set will have this function within it when after you are tokenizing it, and then you are passing the sentences for this training data set as well as for the validation. But in case of validation, we are not going to shuffle it. Otherwise, all the steps is going to be the same, right? Okay, so your data is now ready. Next step is just fine tuning with the keras. Okay, so fine tuning comes in because the pre-trained model is not enough for your specific task, right? So in order to fine tune the model with the process data set, TensorFlow, specifically Keras, we are using would be necessary. You can also make use of PyTorch, but we are doing over here using Keras. So you need to have an understanding of the Keras model objects like compiling functions, bit functions, etc. that we have already done before. Okay, so what we are doing is we are again importing the model, and this is the same thing as we have done before. Here we are specifying the num label equal to 2. Okay, because we are having two sentences to classify, that is either they are equivalent or they are not equivalent. So we have these two things, either it can happen or it cannot happen, 0 or 1. That's why the number of label is 2. It is a binary. Next, from this TensorFlow keras, we are importing the sparse categorical cross entropy, which is the loss function that we're going to use. And what are these? I have already explained it in the previous webinar. So the optimizer we're using is Adam. Then for the loss, we are using this one. And for the mix, I'm using accuracy. So you can think that why are we utilizing this optimizer as Adam? Why we are not using the SGD optimizer over here? The reason would lie in the model pre-training information. So for that, you need to go through the model card and how this model was trained and utilizing which of the optimizers and loss functions would give us accurate results or would give us a good fine-tuning result that we need to see. So this is the model compilation, and then we're fitting the model with our converted data, the TF train dataset and the validation dataset, TF validation dataset. After that, fitting it, since we haven't defined any epochs over here, you can see that there is only, it has ran for only one time and the accuracy is about 63%. Okay, let us now do it for more times. Let's see what will happen. So the number of epochs I expect is 3, the batch size is 10. Here I am using polynomial decay as the learning function. So previously what we were using is this one, this optimizer as Adam. Here we are changing the optimizer a little bit for the sake of proper fine tuning. Now all of this information you have to go through the documentations, but before that you have to first see how or how the model is performing, how the model is behaving with these characteristics. And if it is not enough, you can import this polynomial, just like we have imported polynomial decay, you can import other kind of optimizers, define your own optimizer, define your own loss values, and then you can see how the model is behaving with the changes. So here we are seeing that the initial learning rate is quite high, then the ending learning rate is quite low as comparing to the fall off. And then the decay step is the number of training steps it will take it up. So the Adam, this is the optimizer. In Adam, we are fixing up this learning scheduler that we defined using the polynomial decay. Now, again defining the model, then the loss is the sparse categorical entropy. But in case of optimizer, we are not using the Adam directly, but we are using the changed Adam. We have configured the Adam optimizer and then have used this Adam, the configured Adam optimizer. And after that, we are fitting the model with our data set. So over here, as you can see that over the three epochs, the training or the accuracy has not increased that much. So maybe we can try running for more epochs so that the accuracy increases by learning more and more. But we can see that the loss is also quite high. The loss is not reducing to that much. So this is another again an indication of the fact that maybe this optimizer is not working well for us and we might have to use another type of optimizer. Try utilizing different kind of optimizers for this purpose. However, if you train it for a longer time, you will see that the accuracy, this validation accuracy and the training accuracy will be quite similar to each other and it will give you some satisfactory results. Okay. Last one is the prediction phase. And the prediction phase is the same thing. On the model, you have got the logics, right? You need to go through the max. So we have utilized the softmax function over there from the TF, and the same thing you can do using the argmax. That is, you have the predictions and you need to go through which of the predictions are the highest. You will be getting the argument for that highest one, and thus you will get it. So over here, as you can see, this is the prediction shape of it and the class prediction shape, which is 408. And then by looking into the accuracy, what we see that there are 68% of accuracy. And if you see the F1 score, it is quite high. So next you can make use of these labels and can see how the data set is like, how the prediction is like. That is, when you are passing in this validation data set, it is giving this much accuracy. So you can pass maybe two sentences and then can see if these sentences it is giving out as similar or not. Okay. In the same way, you need to that you have done the tokenization process. You need to tokenize the new data sets and then you can pass it through this model of predict those two sentences and it will do the prediction and then find out the argmax. It will give you either 0 or 1. Okay, so there are 408 records for it. That's why I haven't shown it, but you can remove the print statement and then you can just look into the prints and how it is like. Okay, when you will be running this notebook by yourself. So this is the complete code for it. If you see the complete code at once, this is not too many lines of code, but yes, there are too many concepts to uh, remind yourself about. Okay, and the last one for today is this one that we did before for the sentiment analysis. We have fine-tuned the sentiment analysis, and over here I am using IMDb reviews. Till now, okay, so over here in the first one, while using the pre-trained models, we have just used one or two sentences. In this one, we have used the data set from the low data sets, and here what we are using the TensorFlow data sets. So in the same way, you can make use of your own data. That is, you can just write the same way that we do using the pandas, like pandas dot read underscore csv read underscore excel. You have got your data set, and then you can pass it through the Hugging Face data set that is inside the data set object, and that will convert that pandas data set to the Hugging Face data set, and the rest of the process is similar. So here we are using the TensorFlow datasets, and TensorFlow dataset has got a lot of dataset to explore. Here I'm using IMDb reviews dataset for the purpose of sentiment classification, fine tuning, and this is giving you the information of what the dataset is. And there are 25,000 records, but here I'm going to take just 10,000 because this is quite resource intensive task. And here I have used the GPU, the T4 GPU from Google Colab. And do not try to run this in your CPU, it might hang your system. And even if it is not hanging up your system, it will definitely take about 20 hours or so for just one epoch. So if you are having GPU, then it's recommended to use your GPU. Otherwise, you can make use of this Google Colab. Okay, so this is how the data set is like, and it is going to give you in two labels, zeros and ones. So from transformer, we are importing the word tokenizer, specific tokenizer, then this model as we did as before. And then we are adding the special tokens, that is the same one CLS or recipe will get added if you're just writing it as true. And not only this much, there are many more parameters and the definition for many more parameters are available in the documentation where you can get the best use case of it. So we are utilizing the max length here, we are using the padding. So while doing this, we haven't used the padding over there, we use the data collator, but here we are using the padding. So it completely depends on your use case and how long it might take. For that, I'll again and again recommend you to go through the model card before performing anything. Which is better for your use case is best to look into that model card. Okay, so this is the mapping and we are going to perform the mapping in the same way. If you go through this code line by line, you will see that these are basically the similar steps that we are applying to the way that we have learned. Okay, and at last we are getting this DS train encoded set and the DS test encoded set. Now we are passing it through the TF bird for sequence classification, but this is just for loading it. What we need to do, we need to fine tune it. So for fine tuning, I'm first picking up an optimizer and we are using this Atom optimizer once again. So for bird, it is usually recommended to make use of this Atom optimizer, and then we are defining the loss function, then we are defining the metric and we're compiling. So this step essentially involves your fine tuning procedure with model that you have downloaded. And here we specify the epochs equal to 3. So when we are running the model, that is fitting the model with the encoded training data set, the number of epochs and the validation data, you can see how this is running. So as you can see, the loss is reducing and the accuracy is so high for this. And even for this one, you can see so much of so many minutes, like it's about 20 minutes on an average that it has taken for each of the single epochs, even with the usage of GPU. Okay, so it's quite resource intensive. Now your model is trained and you can look into the prediction of the model. So you can pass on the statement and into this tokenizer.encode, you need to tokenize it. And then the model prediction will give you, then you're using the softmax over here. You can also make use of this np.argmax the way that we have done at last in this project. So here by using it, you see that it is giving you as positive. Okay, picking up the highest argument from this case, it is giving us positive. So you can change this sentence again and then can see what you are getting. Now you can save this to Hugging Face. What you have to do is from Hugging Face Hub, you need to first pip install it. If you're not having it, pip install Hugging Face Hub, then import the notebook login. So once you are just running this one, it will ask for your credential, and this credential you will get by going to your Hugging Face uh, Hugging Face project, Hugging Face interface basically. So if you go here and you go to the settings and then to the access tokens, you will get your tokens. I'm not going over there because access tokens are kind of private and you shouldn't share with anyone. So giving your tokens and then you just need to write this model.push to hub. You can pass your model name and the tokenizer push to hub. You can pass your model name and it will do it for you. In my case, I have pushed this one, this word binary sentiment analysis, this specifically this one. When I pushed it, it has all the files and versions stored here for me. The main advantage is that I do not have to store it in my local system and then I can call this from anywhere I like. What you can do is that you can create one Streamlit app just like this, where I have taken up my model. This is the model path that I have taken up from the Transformers library in the same way that we have done to import the other pre-trained models. This is your pre-trained model basically. So you can copy this and then pass it through this checkpoint in the same way that you have done for the pre-trained ones. And these are the label mappings that you can define it. And this is basically going to start a Streamlit app for you. How the Streamlit app is like, something like this. So you can write the sentences in it and it is going to give you can click on this analyze statement, it will give you the predicted sentiments, which you can even download. Okay. So that's how you fine tune, that's how you utilize the Streamlit application for observing how it is like. And this is how you are pushing your model to the hub. So you are basically open source contributing your model. And if you're not satisfactory with the results, you can go through the Keras documentation for fine-tuning the transformers that will again show you the addition of multiple layers, the way that we have seen before, that is model, the way that we do, that is tf.model.layers.tf.keras.layers.sequential, and inside of it you are passing on the different dense layers. You can make utilization of that as well if the necessity comes up, okay, for the fine-tuning purpose. So here our project set ends. Now you know what the data sets are, you know what the data pre-processing are, the data set.map, we have seen how it works and how efficient that is. We know what the data collateral is for the padding purposes. And then we did the model fine tuning, we did the predictions and evaluation, that is the accuracy, we have checked it. And these are the complete list of steps that you need to follow and that we have followed. And this is kind of quite easy because all the mathematical calculations are being handled by the function APIs that the transformer module and the Keras module is providing to us. We just have to make use of it efficiently. Okay. So that concludes our session for working with LLMs. I'll switch back to this interface. If anyone have any questions or any doubts regarding the projects that we have seen or regarding the LLM concepts, please feel free to ask. Okay, so since I'm done with the presentation and the project showcase, I'm stopping the screen share. If you have any questions, please do ask. Okay, I think there is no question to take in. Maybe we can conclude here. Am I audible? I hope I'm audible. Is anyone there from Innovit?
Yeah, thank you. I think we are good to stop the session. I hope everyone's doubts are clear. So we can stop the session.
Okay, sure. Thank you.